Hi all, this lecture is on measures of relative standing or measures of position. We will look at how one observation ranks relative to the others. Measures of position are especially useful when you're comparing two values of different scales, like if you're looking at ACT scores versus SAT scores. How do you know which one is a higher score? Well, one thing you can do is look at your percentile because that's what they usually report. They may say you are the 98th percentile, which means you did better than 98% of everyone else. Another way you could do it to find out which score is higher is use z-scores. So there are two ways of measuring position, and that's through z-scores and percentiles. We have seen z-scores before, twice actually. We have seen them with empirical rule and then again with normal probability. Z-scores are just the number of standard deviations above or below the mean a number lies. So if your z-score is 1, that means you are one standard deviation above the mean. Whereas a z-score of -1 means you are one standard deviation below the mean. So negative values mean below the mean and positive values mean above the mean. Here's the z-score formula like we have seen before, where you're converting using x minus the mean and then divided by the standard deviation. I didn't put the symbols for the mean and standard deviation because this formula is true for the population and as well as the sample. So here is the previous example about the ACT and SAT scores. The mean SAT score is about 1500 on a scale of up to 2400 with a standard deviation of 30 or 300. So this student's score was 1850. Using the formula, we plug in the 1850 for x and then minus the mean, which is 1500, and then divided by 300, which is the standard deviation. And we get 1.6667, which means he scored more than 2/3 standard deviation above the mean. Now for the ACT score, the mean score is 21 and the standard deviation is about 4.7. So we take his score of 26, then minus the mean, divided by the standard deviation of 4.7, and we get 1.0638, which means he scored 1.0638 standard deviations above the mean. So 1.6667 is a little bit bigger than 1.0638. Therefore, the SAT score is better. Again, when we talk about percentiles, we're talking about the percent of observations that are below that number. So the 73rd percentile on a test would mean that you scored better than 73% of all people who took the test. And keep in mind that does not mean you got 73% of the questions right on the test. For instance, the score of 98 out of 100 could be the 73rd percentile. And here are a few, this is the formula, and then here are a few examples you can go through if you need more clarification on percentiles. Okay, so now for quartiles. Some specific percentiles are the first quartile, which is the 25th percentile. It's denoted as Q1. And then the third quartile, which is the 75th percentile, it's denoted Q3. And then the inner quartile range is just Q3 minus Q1. By the way, the second quartile would be the 50th percentile, which is just the median. So we use these quartiles to determine which values are outliers. So this is a little bit different from what's in your book. You can use standard deviations to determine outliers, or you can use quartiles. I like quartiles since outliers do not affect the percentiles, where they do affect the standard deviations. So to me, I don't want to use a measure that's affected by outliers to determine whether it's an outlier or not. So I would prefer quartiles. So to calculate the lower fence, it's just Q1, the 25th percentile, minus 1.5 times the inner quartile range. And it's always 1.5. That's how it's defined, the formula is. So, and then the upper fence is just Q3 plus 1.5 times the inner quartile range. And you determine what's an outlier by looking at any observation in the data set that's below the lower fence or above the upper fence. So if we look at the example of waiting times in a bank to be served in minutes. So the first person waited 8.35 minutes, while the second person waited 3.82 minutes, and so on. From StatCrunch, we get the Q1 is equal to 5.55, and then Q3 is equal to 8.36. And then, therefore, the inner quartile range is just Q3 minus Q1, and that's 2.81. So if we calculate the lower fence using the Q1 that StatCrunch provided, we plug in Q1 and the inner quartile range, we get 1.335. And then again for the upper fence, we just plug in Q3 and then the inner quartile range, and we get 12.575. And so any data points that are below 1.335 or above 12.575 are considered outliers. So let's look through the data to see if any points are below 1.35. And we see one right here. Do we see any other? No. How about below above 12.575? And there doesn't appear to be any. So we see one outlier, which is on the low side and none on the upper side. Okay, so data sets don't have to have any outliers, or they can have one or more than one. In the data sets that we use, they'll be small, so I would not expect more than two. And if you get maybe like 5 or so, you probably are doing something wrong. By the way, what do we do with the outliers in the data set? Some people just throw them out. There's a lot of methods on dealing with outliers, but we won't go into that in this class. And then one rule of thumb, though, is look at the outlier to see if it's the result of an error. So, for example, if you're asking how many hours of TV a person watches in a day, and they say 30, you know that's not true because there's not even 30 hours in a day. So that person may have thought you were asking minutes. So if it's an error, just throw it out. Otherwise, keep it. That's for just a rule of thumb. So now let's look at box plots. A box plot shows the median, quartiles, outliers, and then the minimum and maximum within the fences. The box plot we will be doing is referred to in your book as the modified box plot because it shows the outliers. And then, so I use StatCrunch to make this box plot. And these are the waiting times down here. And then if you notice, there's a dot right here. This means the outlier. Here are just some specific features. This line represents Q1, and then this line represents the median, and this line represents the Q3, the 75th percentile. So these three lines always represent Q1, the median, and Q3. And then here we draw the whiskers out as far as the smallest and the largest data point that are not outliers. So if you take the outliers out and then draw the whiskers, and then you put the outliers as the dots. So if you looked at that box plot, you can see where the middle 50% of the data is, and we can see the outlier, and then you can see where the rest of the data is. And it can also be helpful to look at side-by-side box plots so that you can compare two distributions. And that's it for this lecture.